looking and seeing how different animals have their senses. You use your senses to be able to take in information about the environment around you. So we're going to be looking at how our sense of vision works and the biology of your eye, and then also a little bit about how light is working, the different types of light and all. So let's go ahead and get started. All right. So what are the 5 human senses? We've got some big models here. We'll see if Phoebe can explain a little bit about them.
In most animals, the brain is the center for processing all senses. Humans have 5 senses. We receive signals from our eyes so that we can see, signals from our skin so we can feel touch, signals from our ears so we can hear, signals in our nose so we can smell, and signals from our tongue so we can taste.
So if you think about all your senses, how much information everything takes in every day. So what happens with these senses? You take in the information and then it has to go to where to be centered out, to your brain to be made sense of, right? So first of all, let's look at this sense of taste. These are just some funny pictures as some little kids are tasting things. The 2 on the left here are tasting some lemons. Whoa! And look at this one. It takes a minute to kick in. And then this one is a lime. See the green lime? So have you guys ever tried those super sour patches and things? Makes your face make that because of your sense of taste. It's super, super sour. All right, we've also got the sense of smell. Now, again, some people can have a sense of smell that's stronger than others. During COVID, that was one of the things that happened with people is they lost their sense of smell. Now, if you look at my first picture, if this is the face that someone was making, would they be smelling something that smells good or something bad? Something bad. All right, look at this face down here. Is this the face of something that smells good or bad? Probably something good, like maybe if you had smelled some cookies that were cooking, that would be good. All right, and then look at this little face over here. Oh no, smelling a stinky foot? Yeah, probably doesn't smell good. All right, how about the sense of hearing? Now, you see this little kid putting his hands behind his ears. So if you've got big ears like an elephant or a deer, then you can hear a little better. Since you guys are having a hard time hearing me, try just listening with I'm talking like now with just your regular ears. Now put your hands behind your ears. Does that make it sound any better? What it's doing is collecting those sound waves. Sound waves are physical waves. So they're coming in through your outer ear. Here comes the sound wave. Comes through here. That's your eardrum right there. And this is one of the smallest bones in your body right through the ossicles. The cochlea, this is the part that helps you keep your balance and all. Now these physical waves are then turned into these electrical impulses and again go to your brain for your brain to make sense of what you are hearing. All right, let's look at this last little video over here. I guess that's that kid's favorite song, right? They were sitting just fine until they heard it and started dancing. All right, so another sense that we have and other animals have is a sense of touch. So look at that little lizard at number 1. Why is he lifting his feet like that? He is a lizard that lives in the desert. So that sand is probably very hot, high temperature. And again, he's resting his feet at different times. Look at picture number 2. You've got a person that's tickling. Now, sometimes it's hard to catch your breath if somebody's tickling, but even as a little baby, they know that that feels funny. Now, look at picture number 3. Did you realize that a turtle with that hard shell, that hard carapace, that carapace has lots of nerves in it so that it can feel everything around it? So even with just a small toothbrush, that feels good to the turtle, and they're getting a good scratch out of it. So a lot of people think that that hard shell doesn't have any nerves to it, and they can't feel anything, but they can. All right, so now we're down to sight. Sight does require light. Now, if you look at my first picture here, we've got this little lizard, and look at how its eye changes. When it's dark, the pupil in the middle is very big. When the light comes on, what happens to the pupil? It gets smaller. See how much that changes? All right, now that type of pupil is needed for that animal. They've adapted to have that kind of vision. look at your pupil at picture number 2. Now, what happens with yours as you see the light come near it? What happens to your pupil? It gets smaller too. So that controls how much light, just like a camera does, it controls how much light is getting into your eye and how it can focus. All right, now look at number 3. So this little kid's coming out kind of in the shadows in the back. It comes out to a bright room. I don't think he wanted to see what was in that room, right? He turned right back around. Whoa. All right. So again, it is your brain, though, that makes sense out of all your senses. Now, different parts of your brain have different purposes. Everybody right now, take your fingers, put them on your eyebrows, and then put your thumbs underneath your ears. Everything behind your hand is brain. So reach around with one hand and feel how large of an area that is. You have a beautiful, big, giant brain with lots of wrinkles. The more wrinkles you have, that's the more intelligent we are. So we're going to compare our brain to a few other animal species in just a minute. But if you look at this brain, the very bottom down here is what we call the brain stem. The brain stem then connects right here at the back of your neck. If you want to feel the back of your neck, that connects then to your spinal cord. Now, your brain stem is responsible for all those critical things like breathing, your heart rate, your reflexes, involuntary movements. Now, the cerebellum right here, that's in charge of balance and kind of coordination. If you look at all these other parts, again, they all play a role. This front part here, the frontal lobe, that's important for language and emotion. And if you look at the back of the brain here, again, it would sit right here inside your skull. You've got this great hard skull to protect it. But if you were out goofing around playing and you fell backwards and you hit the back of your head, you might damage that occipital lobe. What sense would you possibly damage? You would damage your sight. Okay, that's the part that has to do with sight. So again, our brain is encased in this nice hard skeleton or skull to protect it. It's kind of like the main computer though. All right, this is one worksheet that you guys have, and you can do this later if you want. Teachers, if you want that, you get it the same place that we registered. And what this worksheet is showing you are the pairs of the nerves that go all through your body. So your central nervous system, your brain is taking in, making sense of all of these different senses. Again, it's down through the spinal cord, your central spinal cord that's protected by those vertebrae in your back, right? So if you look at my drawing here, though, you've got matching nerves that extend all the way down on each side. So one activity that you could do with this is use a little glue and some yarn and try to make the matching nerve systems that go down. So if any of you have ever had a pain like in the back of your leg, sciatica, that's what a lot of us old people get. We get sciatica. That's because of this nerve right here where it kind of gets pinched around the hip bone. So anyway, so we've got our central nervous system right here, and then our peripheral nervous system is what we call this outside part that's helping us get in, again, all of those senses. All right, so I said we were going to look at some other animal brains, and here we go. So this is looking at kind of nervous system and brains. And if you look at these, I said, remember that we had some very wrinkly brains. So here's our very wrinkly, for a mammal, wrinkly kind of brain. And then look at the bird. Here's our olfactory. Those are like for the eyes. If you look at this for the bird, look at how big their optic lobes are. So for this one, they have probably like an ostrich or something. So they've got big there. All right, so again, some of the same types of parts. Remember, it all goes back through then the spinal cord, that brain stem that comes down. But again, sometimes they're a little bit different. So back over here to our brain, our humans, again, we've got our brain and our spinal cord, part of our central nervous system. Again, you see all the pairs of nerves all the way down. So when your toes feel something, they send that impulse all the way up through your nervous system for your brain to make sense of it. All right. How about an earthworm? Does an earthworm have a brain? Yeah, it has a small brain. And then look at its central nervous system as it goes through. Again, it's got all these different nerves that go off in pairs as well. How about even this, like squids and octopus? Octopi are very, very intelligent. So they do have a very developed brain and a very special nervous system that goes with it. All right, so if we look at this chart, we're looking at humans versus other animals. So in humans, we've got our ears for hearing, our tongue for tasting, our eyes for sight, our skin for touching, and our nose for smelling. Now, other animals have a lot of these senses, but they have other things too. So they've got the ability to use some chemistry. They've got ability to use the magnetic spectrum. So like birds with all of their migrating and even butterflies, they can use sonar when it comes to bats. All right. So again, lots of different techniques that animals use to get their senses and to gather information from the environment with those senses. All right, so back to you. How do you see? If you look at my eyeball up here, so my eye is blinking. Again, you like to keep your eyes moist. What's the function of your eyelashes? To keep things out of your eyes, right? What's the function of your eyebrows? These eyebrows. Those are to keep the sweat and all out of your eyes. Again, a little protection. Now, if you look at the eye itself, the sclera is this white part. And then next you have the iris. The iris is the one that has the color. And then the part in the middle we talked about earlier is the pupil. The pupil is what gets larger and smaller depending on light. So look at your friend sitting next to you and see what kind of colors of the pupil that you have. I mean, of the iris. What color is your iris? Everybody see the sclera, the white part? Okay, so when you are looking out and you're saying, for example, a tree, that light comes into your eye and it goes through that middle part that's getting bigger and smaller, through that pupil. All right, now there's also a lens there. The lens is a concave and a convex, different parts will have light do different things. All right, but as that information comes in through your eye, goes through the cornea right here, that's a lens. Then it goes through right through here. But then look what happens as that image gets to the back of your eye, it's flipped upside down. And that's because, again, the properties of light going through those different lenses. Now that image is going to travel, look, along this optic nerve. Now it's electrical impulses, travels through, and then it gets to the back of your, remember, your occipital lobe back here, so that your brain can make sense of it. All right, so keep in mind how it is that we see. All right, looking at this again, the object is coming through. It's going through for the cornea. Again, see how this is a kind of a, like a cave there? Okay, and then it's got this one too. So it's bending out. This side would be concave. This side that sticks out is the convex. Okay, so it's like two put together. So as light travels through these different lenses, the light kind of bends and wiggles some, and that's why it becomes upside down. All right, looking at this picture, this is an optical illusion that kind of tricks your eyes, what your eyes are seeing, and is trying to trick your brain. So when you first look at this image, what do you see? When I first looked at it, I saw a black vase in the middle, something like you put flowers in it. Black vase. Now, also when I look at it though, I can see two faces, two white faces with a little bit of a black shadow in between. So can you see, if you're looking at the vase, here's the top of the vase, here's the bottom of the vase. I would put my flowers in up here. Okay. Now look away for a minute. Now when you come back, I want you to look for faces. Here's a forehead, here's a nose, here's some lips and a chin. Same thing over here, a forehead, a nose, lips, and a chin. You guys see it? Try it again. Look away for a minute. Come back and look for the vase, just the vase. Look away. Come back and see if you can find the nose and lips. All right, so again, those are some funny illusions that can kind of trick us. Now, when we're talking about light, we are talking about waves of the electromagnetic spectrum. Electromagnetic spectrum. Now, usually you see this kind of diagram when you're getting into like physics and all, but we are looking at the visible light, number 5 right here, That's the visible light that we can see. It's white light. When it's broken apart, we see all these different colors like in a rainbow. But there are many, many parts to this electromagnetic spectrum. Many of you have used a radio in the car. When you're turning that dial, you're changing the frequency. What you're doing is tying into where these radio waves are coming in at different frequencies. If you can find the right frequencies, then you might be able to find your favorite song. Now, many of you have also used a microwave. Now, a microwave is, again, using part of these electromagnetic waves, particularly the microwaves, to be able to cook your food. And it cooks it in a certain way. You notice how the inside kind of cooks faster. Now, infrared you may have used. Anytime you're using a clicker and you go to click the TV on or off or change the channels, that is using infrared. Infrared is looking here at a camera that can tell heat. All right. And again, we've got ultraviolet. We've got X-rays, if you've ever broken a bone. Farther out, we've got our gamma and our cosmic rays. So again, these are all part of the electromagnetic spectrum. All right, but we know that light bounces off of shiny surfaces, water, metal, or mirror. So one way that the light always moves is with reflection. Reflection, right? Everybody agree? You look in the mirror, you're looking at your image that is bouncing off of that mirror. Another way that light can move is called refraction. Refraction is when the light moves through a surface, and as it's going through that surface, it bends. See how it bends? It changes direction. Now, a third way is diffraction. Diffraction is when light moves through a small little hole and then it spreads out. So if you look at my first picture, number 1, see how the light's coming through just a small slit, and then the image on the other side, the light is spread out. So we know that these are properties of light and how they work. Same thing, comes through a small slit and look how it spreads. Same thing down here. So knowing the properties of light, we can again do some funny experiments. What is happening here with picture number 1? This little dog sees his reflection in the mirror, right? And I think he thinks it's another dog. He's trying to get the other dog to play, right? He doesn't quite have the understanding of reflection. He thinks it's another dog. How about picture number 2? Same thing. This little dog sees his reflection in the mirror. And I don't know if he's afraid or happy. All right. How about these? What are these little babies thinking? Look at number 1. Oh, no. Oh, no. He ran right into the mirror and bumped down. All right, look at picture number 2. Oh, he just knocked himself over. Trying to play. He thinks it's another kid and gets knocked over. All right, look at picture number 3. Why is the little kid looking behind the wall? Look, they're going all the way around. They're looking for the other kid. They see their reflection in the mirror, but they don't understand that it's a reflection and not another kid. So she's actually looking behind the wall to see where the other kid is. So again, as your brain learns more, you're able to figure these things out. All right, this picture, look at number 1. Look at the top of this little kid. He's got a small little body, but look at how big his feet are. Is that the same kid? Is this a trick picture? It's just a picture taken through 2 different mediums. So this is using refraction, where the light bends. So it makes the bottom half of his body look a lot larger because it's having to bend. The light is bending through the water versus the air. All right, look at picture number 2. What's happening with his eyes as he pulls his glasses out? It's making them look bigger and smaller, right? So we can use glasses to correct how our eyes see. So if his eyes are not able to see things far away, then he can get glasses that will, again, fix that vision. But again, it does make for funny eyeballs. Again, that was using refraction. Now, this is an experiment Dr. Bloofer is going to talk to you about. See if you can figure out, is this magic or is it refraction? Have you ever done this before? Take a straw, put it down in a cup of water. Notice what happens to it.
Refraction can make us see things that isn't really happening. This straw looks like it is bent. It's in the interface between water and atmosphere. Two different mediums that causes light to refract. So let's take a look up on the top, and we'll notice that we have another perspective. So when you look up on the top, it looks like a regular straw.
So why is that different then? Because when you're looking at this, you're looking straight down just through the air. Okay, when you're looking at it from the side, you're looking through both air and water. So again, that's light. Refraction is light bending. So if we look at our white light, again, when it goes through a prism, this is a kind of prism right here. When the white light travels through a prism, the prism bends the light waves in different ways so that we can see the colors of a rainbow. Now, these colors, if you look to my picture over here, these colors have different wavelengths, just kind of like your radio. The slowest moving waves are the red ones, right? The fastest moving ones are these violet ones. And we call these colors Roy G. Biv as an easy way to remember. So there's red, orange, yellow, green, blue, indigo, and violet. Okay, so again, we are using refraction to break up our white light. All right, now this is a funny machine that we have at the Children's Natural History Museum called a fiber optic toy. You may have heard the word fiber optic. We use that a lot for our internet. So let's let Dr. Bluford tell you a little bit about it.
Fiber optics is a way in which you can move light. Notice light goes the span of the fibers and comes out on the tips. What causes that?
All right, so what she's talking about, see down here, there's a light source down in the middle. But if you look right here, there is no light coming out of the fiber part right here. It's only at the end, at the very, very end, and it's kind of cut at an angle. So how is it that light can only escape from the ends and be trapped on the side there? Let's look at a picture here. So if you look at this laser, the laser shining in, but this rod is made with a material, again, to create the fiber optic. But you see how the laser light is then bending. It keeps bouncing back and forth. So this little rod here has a lot of this ulexite in it. Ulexite is a mineral that a lot of it does come out of California, but it has the element boron in it. And boron is the one that has the property of kind of pulling that image up. Sometimes it's called the TV rock or cartoon rock. But this is what is used to make our fiber optic cables for a lot of our communication and our internets. Because again, light can travel quickly. Here are these fiber optic rods there. So it makes for a fun toy, but we also use it a lot in our professional businesses. All right, so we had reflection, refraction, and now we have diffraction. Remember how it goes through a central point and then it spreads out. Look at the sunbeam coming through. So again, the clouds are preventing that light from coming all the way through. It's got a small area that the sun is able to, the light rays are able to escape. So now it spreads out like an umbrella. Same thing with the colors on this CD. See how it's a small part and then it again spreads out. So that's something called diffraction. Now, if you've ever played with bubbles, you have experienced diffraction because again, the light is traveling through these different layers. As it gets through, the light again spreads out. Now, if you look right here, you see this like a tower that's right side up. Look over here, there's a tower upside down. So again, some of the same properties that we saw earlier. Now, again, we've got layers of soap and water. As those layers tend to drain, you'll see some small little black polka dots, and that's the clue that this soap bubble is getting ready to pop. All right, so again, reminding you of how you see. What is so unique about our eyes? Again, look at all these different parts put together. So we've got the cornea again, and you've got to be careful. Sometimes you can scratch that cornea. Your pupil is what's going to dilate and allow different light to come in. And again, all through your optic nerve. So when we think about other animals, we think about how a bee sees. Okay, they're going to see very different. They have compound eyes, right? So they have larger eyes, but they're compound. So they're seeing some of the same images. Here's a quick video to explain that.
Take the honeybee. Many flowers need bees in order to pollinate. No visits from bees, no pollination, no reproduction, so it's actually a matter of survival. And flowers have had to learn to advertise themselves to bees in a way that bees can understand. Because to the bee, this garden looks very different. For the first time, high-definition cameras can give us a bee's view of the garden, revealing the hidden patterns in flowers that are normally invisible to humans. Patterns that to us are completely invisible. Seen in ultraviolet, new markings appear on the flowers, like secret ink. The markings are caused by special compounds in the flowers called flavonoids. To the bees, they're like aircraft landing lights, guiding them straight into the nectar and pollen at the heart of the flower.
All right, so that gives you a little bit of an idea. Remember that electromagnetic spectrum. I mentioned the ultraviolet quickly, but that's how a bee sees. You may look out and see a yellow flower, but a bee is going to see more of kind of a purple and a white, with one part being very bright that brings it in. All right. Now, looking at a few other animals and the difference between our eyes. If you were to dive deep under the ocean, no, not as much light, right, down there? So this is kind of what we would see, just darkness. But if you were a cuttlefish, this is a cuttlefish that's adapted to living at these deep environments with not a lot of light. You see, they don't have got some eyes there, but not very big. They, again, would allow their other senses to take over, right? But they have adapted to some form of vision without a lot of light available, right? Picture number 2. This is what we see: green grass and a small little brownish gray field mouse. What does a snake see? A snake sees actually through heat. They have an organ at the top of their roof of their mouth. So when they stick their tongue out, they're actually taking in particles and are able to kind of smell, see, taste all at the same time. But they see again through heat. They see infrared. So again, they can see that heat mass. They can tell the difference between the grass that's cold and the little field mouse that's very warm. All right, this is another experiment that you can try, and it's also, again, where we registered. You can, there's a lab write-up that kind of tells you about it, but this was a great experiment that an American scientist, James Gibson, did many, many years ago, talking about learning and interacting with stimulus. There is a lab sheet that you can have go along with it. But in this experiment, you are just going to find 4 objects. The original experiment that Dr. Gibson did was with cookie cutters. Now you'll see here that we've got some little freezer shapes, and then you can also do pennies. So go ahead, Phoebe, and tell them how to do this.
So for this experiment, we're going to be testing sensation of touch in our palms versus our fingers. So you're going to need a partner and 4 items that are different shapes. So what you're going to do is you're going to have your partner grab an item while you don't look and hold your hand out flat. And now you're just going to guess what you think that item is. So I think that's a diamond. And then you're going to keep your eyes closed and move the item to your fingers so then you can feel it. And now I can feel that this is actually a harp. And you can also do the same activity with items like coins. So same thing, close your eyes, hold your hand out flat and don't move it. And then make
Hold
a guess.
it flat.
I think this is a nickel. And now you can move it to your fingers. So now I can tell that it's actually a penny.
Now, what is the difference in this experiment? Do you have more nerves at the middle of your hand or at the tips of your fingers? So again, we're talking about collecting stimuli, how our senses collect information from the environment around us and how then our brain makes sense of it. So one thing that I would recommend if you're going to do this experiment is when you get the shape in your hand, have your hand on the table. If you noticed at first, Phoebe was kind of wiggling it a little bit. So trying to get an idea because you can't tell much. But so leave your hand super flat on the table. And then the next time you're able to then use your fingertips to try to figure out what it is. But this was a great experiment that kind of proved the importance of our hands-on learning because we learn a lot better when we have those stimuli involved. All right, so again, this is the lab sheet, kind of gives you an idea. You've got a couple different trials. First, you're going to put the object on your palm, then you can feel it. And again, you record your results, and then you do the same thing with your partner. So you get a couple tries to do it. And then you can even kind of do a little math down here as well. All right, here is a quick storybook about light magic. This is on the Math Science Nucleus website as well, if you need to find it again later. But here we go.
Light Magic by Joyce Bluford, animated by Doris Rea and Hagos Tewaldi, read by Phoebe Chen. It was getting dark in the house. I reached over to turn on the light. I wanted to read a book. The bulb got bright for a second and then made an explosive sound. It went dark. I was too lazy to get another light bulb. Without light, my eyes got heavy and they wanted to close. I thought I would go to sleep, but in the distance I noticed a caveman. Was it a dream? The caveman only had fire to produce light when it was dark. He only had the stars up above to guide him at night. The sun to early humans was very important because it brought light so they could see. They did not have television or radio, but they did make stories with shadows. This dog would come out at night and... The dog got larger and larger when the caveman got closer to the fire. The dog got so large, it ate the caveman. I woke up thinking the shadow dog ate the caveman. What a way to go. I drifted back to sleep, but then my door opened, and in came an Egyptian who was looking for light. The light bulb in the hall was burning bright, but I noticed she had her eyes closed. "Open your eyes, silly," I exclaimed. "Oh, thank you. I forgot that eyes help you see light. I am a very old woman." She then started to tell me a story about fire and light. One day, when the fire was very, very hot, the sand turned into a hot, glowing glob. They took the glob and let it cool down. It was a substance that you now call glass. They played with it and noticed that it did something magical to sunlight. It produced different colors, like an object we sometimes see in the sky after a storm. The glass created a rainbow. The glass was magical, making colors from white light. The old woman continued. She left and I started to dream about rainbows. The rainbow turned into a man. My teacher always refers to it as Roy G. Biv. R is for red, O is for orange, Y is for yellow, G is for green, B is for blue, I is for indigo, and V is for violet. Every time I look at a rainbow, I always see Roy G. Biv. I mainly see Roy when the rain is just stopping. I woke up again and asked myself, so what is a rainbow? Is it a road for people in the sky to come to Earth? Is it an angel who took up painting? Or is there a scientific reason? I wonder if I could experiment and find out what is going on. I couldn't make a large rainbow by myself. However, I did have a prism that made a rainbow when I shined a light through it. The prism refracts light and breaks it into many colors of the rainbow. Violet rays have more wiggles as it moves. Red rays have less wiggles. All light travels at the same speed, 186,000 miles per second, or 300,000 kilometers per second. That is very fast. So blue has to wave extra to keep up with red. This separates white light into rainbow colors. I guess if I look in the mirror, I should look like a rainbow, but I don't. I am only being reflected, so all the white light moves together. Different types of mirrors can make us look silly. Light is reflected when mirrors are curved, so the light bounces outward or inward. A lake can reflect an image. Any shiny surface can also reflect an image. Light moves all over. It can refract and reflect. It also can diffract, which means it goes through a small opening and spreads out. Light is a magical experience from when the sun rises to when the sun sets. The creation of light inside our homes allows us to see all the time. It is a wonderful world when we have light. We can walk outside late at night, and we don't even have to carry a torch like our caveman friend. The end.
All right, so again, our world is very different since we have the ability to have light. All right, that storybook kind of reviewed a lot of the things that we covered. Also, maybe a few ideas of experiments you can try later on at home or at school. Now, I've got two optical illusions for you here to look at. This first one that right here, we just put some balls in. Why are they not going down the ramps? How is it that they're defying gravity? It's all about perspective. So the ramps are actually going down and meeting in the middle. But from this perspective, it looks like these ramps are going down this way, right? Watch as it spins. So our brain is telling us kind of one thing, but our eyes are taking in information, and sometimes there's some tricks that happen. All right, look at this picture right over here. What do you see? Some of you may see an old man with a bald head and some glasses. Some of you may see a little mouse with his tail curved around and the ears. Let's see which ones you see. So if you see the mouse, here is the nose of the mouth. Here's some ears. Here's the back of the mouse, and here's his little tail that's all going around. Now look away for a minute if that's easier. Now come back and look for a face. Here's the man's nose. Here's his glasses. Here's his bald head, an ear, and his chin. So again, funny optical illusions. All right, these are some great ones too. All right, let's look at this one first right here where my cursor is, where it is about some flying birds, or is it about fish? So as you look at this picture, your eyes are getting kind of tricked between the difference of the dark background and the light background. So as you watch this fish, as it starts to transform, so we're using the white, 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 but then all of a sudden, here's where you start seeing the darker flying birds, right? Fish shape is still there, but now we see the darker birds. So again, this is a great print by M.C. Escher. He was a great artist that does a lot of these optical illusions. All right, now let's look over here. Obviously, it's an elephant, right? An elephant has 2 ears, 2 eyes, 2 tusks, 1 big trunk, and 4 legs, right? All right, check out the legs on this elephant. How many legs does it have? Are they in the right place? When we first look at it, we just kind of glance at it, and our brain is trying to make sense of the picture. So if we look at this elephant right here, we start at the top of the shoulder. This is a leg, right? Oh, no, it's not. That's just an opening, but it should be the leg. Over here, this is the other side of the shoulder leg coming down, but wait, is it a leg? It should be. Instead, the leg is at an opening. All right, let's see if we can find this back leg. Should be here. but they morphed it over here. This is the other hind leg, the other side, but it's not there either. So isn't that a funny optical illusion?